Thank you very much. So I'm going to start sharing my screen, and you will see that I'm going to try and cover 3 topics today: case estimation, perspective taking, and visual place recognition. Just a little bit of admin before we start. I think I'm happy to take questions after each of those sections, just the most important ones, or well, a couple, and then I hope there's more time at the end for overall question time. My background is in robotics and computer vision, and I also try to use computational neuroscience and computational psychology and incorporate that in my work. And as you said, I just joined QUT a couple of months ago. So most of the work which I'll present today is done at the Personal Robotics Lab at Imperial College. And then the last couple of slides is quite recent work, which hasn't been published yet at QUT. So let me dive into perspective taking, which was the overarching kind of theme of my PhD thesis. And while it's a conversational thing to say, oh, I've taken your perspective, I'd like to just briefly introduce or define what I mean by it. When I talk about perspective taking, I mean the ability to assume another person's visual spatial viewpoint. So I'm interested in visual cognition, so visual perception, and there are 3 components to perspective taking. It's a perspective taker, which in my case is the iCub robot. It's a target agent, so a human interacting with the robot, and 1 or more target objects. And you will see that in this picture there, the object of consideration is perceived differently by the robot and the human, and the robot has to know that there's a difference in perception in order to interact efficiently with the human. And psychologists have found that there's 2 different levels of perspective taking. So one is just knowing whether the other person can see that object, and the other one is acquired a little bit later as a child, when they're around 5 years old, and it gives them a spatial understanding. So what is my left is your right, and it gives you a visual understanding as well. So if I have a bottle in front of me, it looks differently from the front and from the back, and at some point we acquire that knowledge. And throughout my PhD, I tried to get this knowledge to adapt it for the iCub humanoid robot. And there's a variety of other applications. So if you think of action recognition, if you perceive an action, then typically for you as a human, it doesn't really matter whether you see a person doing an action from the front or from the back. You will still recognize that action. And language understanding is very important. As I just said, my left is your right, my front might be in your back. And for a robot as well, in order to plan a path, the robot should know where the human is headed next. And in my first piece of work, a couple of years ago now, I provided a system which can take the perspective of a human without any artificial markers. So previously, the human needed to wear, some weird helmet on, such that it could be perceived where their head direction is facing, or some glasses as well to know where they're looking. Whereas in my goal, it was always to not equip the human with any artificial sensors, and just use the eyes of the iCub to solve the problem. And there's 3 basic components which are required for perspective taking. So it's object recognition. You need to know which are the objects of interest. gaze estimation, which is going to be the second part of my talk. So that's just telling you where the human is looking. And you also need to have an understanding of the environment. And once you do that, you can then do the level 1 and level 2 perspective, which I introduced in the previous slide. So to give you a better idea, I'll play the video. So here you can see with those little bubbles, they show you whether an object can be seen or not. So it's tracing a line of sight from the human's head to each of those objects. And if the line of sight is interrupted, the robot knows that this object can't be seen. And then it takes that into consideration when interacting with the human. And here we now see that the robot can also kind of approximate the gist of the scene on how it's perceived by a human. And that gives you an idea of this left-right understanding. So this is the brief kind of the basic understanding of what's going on there. And I'd like to talk about more on the gaze estimation part. That's going to be the focus of this talk. And gaze estimation, so in the first, in this work, you will have seen that I've just taken the head pose into consideration without using the eye gaze at all. But it's really important to consider the eye gaze as well. And why is it important? So if in a typical conversation, if it's not via Zoom and we were sitting all in a big room, then your eye gaze would tell me how much attention you pay to what I'm saying. Or if you have a group conversation, the eye gaze is also an indicator on whether or not it's my turn to speak. And if I ask you to recognize an object from, an action from another person, and if I occlude the eyes of that person, then it's much harder for you to recognize the actions. And there's also a little fun application, and it's been shown that you can kind of predict whether one person likes another person in a date, just based on the eye fixations. So if they look more in the other person's eyes, then that means that they're more interested, rather than if they look at other parts of the scenes. And as with many other applications in computer vision, eye gaze estimation recently has been tackled with deep learning approaches. So I hope most people are familiar with deep learning. It's a machine learning technique where, given an input image, you learn a network, you train the weights, and then the output in this particular case is the angle of the eyes. So whether I'm looking up, down, left, or right, that would be the output of this network. And those deep learning approaches have been really, really successful. However, they have one big drawback, in that they require a huge amount of training data in order to train those weights. And it's no different for eye gaze estimation. So in the literature, what people have done is they ask the subjects to look at a laptop screen, and then on that laptop screen, or well, here it's a computer screen or tablet screen. But the idea was always that they asked the subject to look on a marker, and then the marker moves across the screen. And every time the marker stops, you look at the marker, and then the subject has to press the space bar, and that gives you one training example. So at this particular point, you would exactly know where the person is looking, because you know where the marker is on the screen. And you also have the webcam view of that person. The problem with that is that it's very limited in the appearance. So you see, if a person is sitting in front of a laptop, they always look more or less straight at the laptop. There's not much head pose variation. It's quite a standard setup, and the same goes for tablets. In the tablet scenario, there's more lighting variations, but still it's quite limited, and the camera subject distance is really close. However, in my work, the aim is to do eye gaze estimation in human-robot interaction scenarios where there's a much larger distance between the camera of the robot and the one person or multiple persons who are interacting with the robot. And the question was, how can I collect the data set that allows me to collect these training data without having this cumbersome issue of having to show a marker and then having to move that around. So the way I tackled it is that I set up a pipeline where you have a motion capture camera, well, multiple of those in the room. And those motion capture cameras allow you to very precisely track some little markers. They're little balls, roughly 1 cubic centimeter. And it allows you to follow them around. And what I've done is that I created some eye tracking glasses. So they're just, similar to sunglasses, except that they have some small cameras well, right behind where your eyes are. And those glasses allow you to track the eye gaze very precisely. So now knowing the head pose from the motion trackers markers and the eye gaze from the cameras, which are really close to your eyes, it allows you to, in real time, estimate where you're looking. So here you see the setup where I wear those glasses, which have this yellow frame. And you will also see, hopefully, that there are some gray motion capture markers. And the red little line shows where I'm looking at this particular moment. And that has the advantage that it allows you to annotate the gaze vector at any time, in real time, in free viewing conditions, and the person can look around without having to look at any particular target. So the person can just, can go on with their normal daily life, let's say, and I can still capture those training samples. And another advantage is that I don't show it here in this video, but I could even turn around and have my head, the back of my head to the camera, and I could still annotate gaze samples because the motion capture markers can still see the glasses. So the problem with this approach is that now the subject is wearing these glasses with the yellow frames. However, if we train a deep network with those images where the glasses are worn, it's very easy for the deep net to overfit on those particular samples where glasses are worn. Whereas at inference time, when you're actually interested in what the person is looking at, we obviously don't want the subject to wear those glasses. So because I have a model, a 3D CAD model of the glasses, I can overlay that model on the particular image, which gives you the masked image in the middle. And then there's another deep learning technique called generative adversarial networks, which allow you to generate images based on a set of images and then pick one which looks similar to a target image. So in this particular case, what I've done is that I asked the subjects to first look around while the glasses are being worn. So that gives you some images in one domain. And then another couple of minutes, the subject is recorded in the same kind of environment without those glasses. And then you can map from one domain where the glasses are worn to another domain where the glasses are not worn. However, if you just use the generated image, so that's the third image at the bottom from the left, then that would have a different gaze, which is not desirable. So what we do is we only in-paint the image, so that's on the right-hand side. We only in-paint the red area. So we preserve the gaze and in-paint only the area of the glasses. And then that gives you a realistically looking image of the subject without those glasses being worn. If you look carefully, you will see that there are some artifacts. However, we've noticed that at inference time, it doesn't really cause any issues. So what's cool about this data set is that we provide a large training set for gaze estimation techniques in kind of medium distance scenarios. So further than the screen setting, but not as far as, I don't know, a surveillance camera in a supermarket. It's really the only data set which provides you with head pose annotation and eye gaze annotation in those kinds of settings. And if you're interested in applying this technique, it's available for download. There's a package available. You can download the data set as well as the pre-trained model, and you can run it really, really easily on just an image. So the question then is, given this data set of training images, how do you actually train the deep neural network? And there is, I don't want to go into too much detail here, but the trick is that rather than using a single network, we train multiple networks which are initialized with different rates and train them with the same training data. And you find if we then average the predictions of those different networks, the average prediction outperforms each of the individual models. And that's a recurring theme kind of which I found in my work, and which you will see later on when I talk about visual place recognition, the work I'm doing currently at QUT. We see that if we average the predictions of multiple networks or different input images, they seem to work better than individual networks. So at inference time, so at top you see the training pipeline, which is quite complicated with those eye tracking glasses and the generative retrieval network, and then finally the gaze estimation network. However, at inference time, at the bottom, all you require is an image where a person is being present and the head is visible. And that image can come from various sources. So it can be just a webcam on your camera. It can be a camera from a robot, or it can be a Kinect, or whatever you can imagine. And you can apply network on these images, and it will provide you with the head pose and eye gaze. So that has a let me talk about the results first. So what you see here is in red are the prior works, and you will hopefully see it's an animation. So without in-painting, you will see that all of the methods perform worse. So if you just use the input images where those yellow classes are visible, then the method doesn't perform as well as after removal of those glasses and then training the networks. And in general, you will also see that our proposed gaze estimation network performs roughly 10 to 20% better than the state of the art in a variety of experiments. So on the left-hand side now, on the top left, you will see a subject in the kind of setup we use. So there's a couple of objects visible on the table, and the subject is just randomly looking at some of them. And in the inset, you will see the estimation of the eye gaze. And same as at the bottom. At the bottom, I go for extreme eye gazes, just so it's easier for you to see how the performance of the method. So the red line in this case just shows my eye gaze. And then you can do cool things. So what we've done there is that we mounted a laptop on a wheelchair, and then the subject is just required to look to the left, and then the wheelchair is turning left, or look to the right, the wheelchair is turning right. And when the subject looks up, then the wheelchair goes backwards, and there's just this mapping of gazes. And you will see that without having to use any hands or any other kind of input, the wheelchair can be controlled quite reliably and nicely. And that's, we think, very important in the medical context, because for many disabled subjects who have muscle weaknesses, the eyes are the last muscles which still work for them. So controlling a wheelchair with the eyes is very, very, of advantage for them. And what's even better is that you can also show that the method performs in completely different setups. So here, if you're a little bit familiar with computer vision methods, they often work in kind of similar scenarios, but then they fail miserably if you change the lighting conditions, or if you go to a very different environment. Whereas with our method, it's robust against those changes, and we've shown that you can use them outdoors in the direct sunlight, and they still perform really, really well. So this is here what I've just said qualitatively. We can also show it quantitatively. So what happens if we train a deep net on our data set and then just apply it without any fine-tuning on images where that are captured from a laptop camera? And we see that ours again outperforms the state of the art by quite a margin. So 7.7 degrees compared to 9.9, where those particular images were never seen by the data set. So up to that point, I'd like to have a brief break and just ask whether there's any questions for now, maybe just one or two.
Tobias, I can ask a question there, if it's okay. On slide 13, you mentioned robustness. Can you elaborate on it? What do you mean? Because from my perspective, the methods are the same. It seems like an artifact of the data sets, or am I missing something?
Absolutely, yeah. No, with all those deep learning methods, the trouble is to get a data set which captures a wide variety of, in this particular case, eye gazes and different input images taken in different lighting conditions with different head poses, different variations in the particular camera being used, variations in the distance to the camera. And if you don't capture those variations at training time, those methods often fail at test time. So yes, it's a matter of the, mostly a matter of the data set that is being used.
Okay, yep. Igor has just typed a question if you open your chat.
Sure. What about blinking? That's a very good question. So I took out the slide actually, but if you're interested in blinking, I will just provide you that slide. That's great that someone is asking for blinking. So let me unskip that, and blink estimation. There we go. There's a whole slide for it. So I didn't want to talk about it just because of time constraints. But blinking is very, very important. And if you don't detect the blinks, then those methods fail, and they just provide you a random estimate of the gaze. So you have to detect blinks, and the good thing is that we can use the very same data set, because we can annotate blinks in that data set as well, and then similarly train a deep network to detect those blinks. And again, we can do the ensembling methods, and we show that we outperform the prior art on blinks as well. And then if we combine the blink and gaze, we can have a the aim is to finally have a unified framework where rather than having separate networks, one for the blink and one for the gaze, we'd like in the future to propose a unified framework which allows you to estimate the blink and gaze within a single method. But for now, what we have is a separate network which detects blinks and then informs the gaze estimation network about those blinks. And in this case, there's no need to estimate the gaze, because the estimates wouldn't be reliable. Does that make sense, Igor?
Okay, and just
yes, they do.
Yep. Okay, we have 2 more questions, and let's just draw a line under these 2 questions. We can come back to it later. One is how quickly you can do stuff, given you have 3 neural networks, and then there is one question by Chris. I haven't read it yet. You can read it later.
Yeah, so about the frames per second, we've done quite a few optimizations there. So it runs in real time. It runs around 35 frames per second with up to, I think we tried 7 subjects at the same time. So it works quite quickly. And then the questions about the significance from a 1 to 3 degree improvement. It is quite significant if you think about, well, it obviously depends on the distance to the particular object of interest. So in, I think in 1 meter distance, it's a difference of roughly 10 centimeters or something like that. So if you have, if the objects are well separated, then 1 degree difference doesn't make a big difference. However, if you have multiple objects close together and you want to know which particular object the subject is looking at, then a 1 degree difference might make a big impact on the performance. Cool. All right. So now I can't get out of my chat. There we go. Okay. So now I'd like to talk about perspective taking in a little bit more detail. And what I've done there is I proposed a computational model for perspective taking. So this is quite different from the previous work, which had a practical application in the gaze estimation. What I really tried to do in this piece of work is understanding how humans take the perspective of other people. And there's a lack of computational models with that respect. And what really puzzled me is the setup you can see on the right. So what psychologists have done is they ask subjects to estimate whether an object, so in this case it's a gun and a rose, don't ask me why those particular objects, but they tell you gun, and then your task is to press with the left button if the gun is to the left of the other person, or the right button if the gun is to the right. And you see that it's becoming increasingly difficult. So in the bottom right graph, at a 0 degree angle, you're really fast in doing that. And then the higher the angle of rotation, so that is in the bottom middle image, you see if you clockwise or counterclockwise change the angular disparity, it becomes increasingly difficult for you to do that. So that's, I think, intuitive so far. What's not intuitive or what was not intuitive to me, is that if you change the position of the person sitting in front of the screen, either just rotating the body to the right and still looking at the screen this way, or to the left and still looking at the screen, straight at the screen, that has an impact on the performance as well. So if you rotate right and the person is to the right, the person whose perspective you want to assume is to the right, then you're faster than if you are rotated to the left and the angular disparity is to the right. And that really puzzled me, tried to find out how this could come, where this could come from. So I formalized what they call the embodied transformation account. So it's quite a simple thing, really. What it says is that perspective taking is the emulation of movement. So you imagine to move to that other person's perspective, rather than actually moving to the other, physically moving to the other person's perspective. So from a robot's point of view, it's a matter of executing a command, or just thinking about the command and then simulating what that command would look like. So in the simulated setup that I've got is I used two simulated eye cups, and the task for one of the eye cups is to take the perspective of the other eye cup. So you see the different, the same scene perceived by the two different robots in the middle. And then you can vary all those different parameters, which I just showed in the previous slide, very easily in the robotic setup. And the architectural overview is as follows. So with F, I denote a forward model. So a forward model allows you to estimate what the state of the robot would look like. So the state here is the physical position, so X, Y, and the angle of the robot. So it's just really, really simplified. And U is the control command. So going forward, going backward, moving left, moving right, rotate left, rotate right. And then that state Z, well, ZI, you can compare that to the target state, Z hat, from the target robot. And after the comparison, you get a bunch of difference vectors. So how different is the estimated pose from the target pose? And then you just execute the you simulate the control command that gives you the lowest estimated difference. And then you do that in a loop. So after you thought about this, after you simulated that movement, that gives you a new estimated state, and then you can feed that in a loop, and just do that until the difference between the estimated state and the simulated state is small enough that you can stop the estimation. So to measure that distance d between the estimated state and the target state, you can think about a variety of distance measures. So the two, I came up with two here which are relevant. So the first one is the comparing each individual state. So that is, if you think about just the head pose and the eye gaze, is my head rotated to the left and my eyes looking to the left, or is my head rotated to the left and my eyes are looking to the right? So both of them have to match. So the head as well as the eye gaze in this particular case. Or, so you will see that this is task error. It's not relevant for the task, because it doesn't matter why, if I rotate my head to the right but keep looking at the screen, I will still perceive the scene in the same way than looking straight at the scene. So that's the second term there, weighted by omega. This is just the gaze direction. And now you can vary that omega, and that will be important later on. So if you run this model, you can then compare it with human data. So in the very simple setup, you don't vary the posture of the robot who's taking the perspective of the other robot. And then you can see how many times do I have to go in that loop. That's the artificial response time. And you can compare that to the response time of the human in milliseconds. And then you will see that human data and model data matches really well. So this, so far, because there's a linear increase, you could have thought about 100 different ways of taking the perspective and could have always gotten that linear increase. It's getting more interesting here, where we can now have those congruent and incongruent postures of the robot. So congruent means, if you look at the top left, that the head is rotated to the left and the target robot is to the left. Whereas at the bottom, the head is rotated to the right and the target robot is to the left. So that means they're incongruent. And now you can again compare the model data with the human data, and you will see that there's running a variety of statistical tests. You will see that there's a high similarity in the statistics. And you can take it a step further by doing posture congruence. So what you do now is you not only, as in the previous slide, I only varied the posture of the robot that is taking the perspective of the other robot. What I do here is now I vary the posture of both robots. So if they both rotate their head to the left, it's congruent, or if one of them rotates to the left and the other one to the right, it's incongruent. And you will again see that there's similar statistical properties in a wide variety of experiments. And now the last bit what I want to show you here is that you can also consider individual differences. So when humans do these experiments, some humans are really, really fast, other humans are a little bit slower. And for some people, there's a higher difference in response times between the setup where they look straight at the screen and when they rotate the body. So for some humans, it doesn't have any impact at all, whereas for other humans, that there's quite a large impact. So now if you draw that omega from a standard distribution, you can replicate the effects observed by humans. And I split it into, so that's something which psychologists have done. They split it into females, males, and the overall group. And I can replicate the statistical properties again, just by slightly varying the mean and standard deviation of that omega for females and males. So that's just me replicating the data which has been observed in humans. So that shows that not only on an individual level there's a high degree of similarity, but also on the group level. And now, because you have the model, you can also predict a variety of cases. So just going to talk about the first one for the sake of time. So what happens if you force a response early before the person is actually finished taking the other perspective? And then you will see that the model predicts that leads to an egocentric bias. So you're more likely to give the answer that, so if there are those two objects, you're more likely to respond the way that you observe those two objects, which is really hard to do with humans because you can't really force a human to press a button at a certain time. However, psychologists have come up with a way of kind of a trigger of doing that. and that was post the time we published the paper, and they've shown that this is actually the case. So that was really nice to see. So there was a lot of talk about Imperial, and considering the time, I think we'll wait for questions till the end. The remaining 10 minutes or so, I'll talk about recent work at QUT. So this slide just shows an overview of the robotics group, now the Center for Robotics at QUT. So you see there's a really, really wide application area that is considered at the QUT Center for Robotics. So you see it as agricultural robotics, we do autonomous cars, we do human-robot interaction, we do surgical robotics, we do underwater robotics, we do a lot of grasping and picking, and I'm involved in the MURI project, Neuroautonomy, where we're looking at neuroscience-inspired perception for spatial awareness for autonomous cars. So there's really a wide variety, and if you have more questions about the work there, I think Michael can give you a couple of hints after the talk. But I want to talk about visual place recognition, which I started looking at. And the task there is that given a data set of images that you've observed in the past, you want to know whether, given a query image as well, whether you've been at this particular place before, and if so, which place that was, or whether you need to add that image to your data set, whether it's a new place that you haven't been before. And that has, again, a really, really wide application area. So there's this hospital floor. Well, my wife just gave, we had a little son half a year ago, and it's horrible to navigate in the hospital because everything just looks the same. So it would be really nice if you could get a hint on where you are. In autonomous cars, there's there's certain parts on the world where you don't have GPS, so in tunnels would be really good to keep track on where you are there. Or underground, in mining, for example, you have to recognize where you are within the environment for any kind of navigation you want to do. And the way visual place recognition is done is that typically you extract some features from those images, and then you use some kind of similarity metric. So here it's the cosine similarity to pick the closest feature that you've observed before. And then if that's below a certain threshold, then you know that that you've visited this place before. So there's a difference matrix in the bottom left, which shows you on kind of each entry of the matrix is the difference between the reference image and a query image. So in this case, there's around 300 reference images, and then you have the kind of same traverse across on the query. And what you are hoping for is that the diagonal shows a very low distance, which would mean that you always have a good match between, so reference image I corresponds to query image I, which is by design, and that would be of advantage if you get this performance. So the way I want to tackle visual place recognition is using event cameras. Event cameras are a novel type of sensor, so they operate very, very differently from a normal camera. So a standard camera, you get a frame every 33 milliseconds typically, whereas with a event camera, as you see in the bottom, you get this continuous stream of events. And if nothing changes in the environment, you don't get an event. So an event is the XY coordinate of a pixel, and the time and the brightness change, whether the pixel got brighter or darker. That's got a variety of advantages. For example, you don't observe motion blur that you have typically in frame-based cameras. And then, oops, sorry, I shouldn't have. So what it looks like in practice, hopefully, oops, you see in the left in the inset how it looks like. So red means that the pixel got brighter, and blue means that the pixel got darker. That's kind of the output of an event camera. And what you can do nowadays is that you can, then it's a little bit counterintuitive, but you can reconstruct frames from those events. However, those frames have a couple of advantages as well, because there's, they have a really, really high dynamic range. And as in the left observed, there's no motion blur either. So you can reconstruct these images, and that's been done before in another group. I should mention all of those videos that you observed there. And what's really cool there is that if you look at really bright scenes, the frame-based representation you'll see is, it suffers from artifacts, whereas on the right you see the reconstruction looks really, really nice and clear. And the way they do that is that they consider a certain number of events, and for those events, they feed that again to a deep network. So you see a pattern there, which provides you with an estimate of the intensity image. And the way to do visual place recognition with that is that given these reconstructed images, you can extract the features, and you again have your data set, and then you can do again just a normal comparison between the features in your data set, in your database, and the query image. However, what we observed is that if we now change the reconstruction parameter, rather than just using events of a size, event windows of size 2 to reconstruct those videos, you can vary the number of events in each window to reconstruct the images. And here I should mention that they're just numbers to play with. So typically we talk about tens of thousands of events to reconstruct a single frame. You can do that, and if we average the predictions of each of those different window sizes, or you can also just use a normal time-based approach and consider however many events are in that particular time window, then that results in a better visual place recognition performance compared to just using a single reconstruction or a single set of reconstructed images. So this is just here some quantitative results on the left. So you'll see that there's one line off the bottom, which is the frame-based approach. So you'll see that each event method performs better than the frame-based approach in this particular case. However, it has to be said that this is a really low resolution normal frame camera. So if you were to use a high-end frame camera, that would perform much better than what you see in this graph. Then there's a lot of dotted lines, and each dotted line corresponds to an individual method. And then I just wanted to look at the black line, which is the ensemble method, where I averaged the predictions of each of those individual classifiers, kind of. And on the right, we see qualitative results. In the top two rows, we see challenging cases where the ensemble method performs, or retrieves the correct match, whereas the individual methods don't. And in the bottom two rows, you will see two failure cases. And I think it would be interesting as well, just talking about future work, which I'm planning at QT, and we would be really happy to collaborate with other unis there. One of them is on viewpoint hallucination. So in this visual place recognition scenario, you can imagine that if you have a particular image and your data set of images, what happens if you don't find if you have multiple hypotheses on where the place could be, but they all slightly are varied in the viewpoint you consider the same place. Can you imagine how the place would look like from that other viewpoint that matches the data set image? So that's one question which we're asking. So as humans, we know pretty well how the environment would change if, in this case, we steer to the left or we steer to the right. We kind of have an instinct on how the environment would look like. And the question is whether this viewpoint hallucination would help in visual place recognition. And then the second point is that we are about to receive a ClearPath Jackal robot equipped with really cool sensors. And the question is, rather than hallucinating as above, can we actually pick the next best viewpoint and go there that allows us to maximize our chance of getting the correct match for visual place recognition scenario? So in the bottom right, you see this kind of scene exploration. So what have you seen before? And what would you observe if you move to a new place? And again, we are hoping that this will provide us with a means of increasing the visual place recognition performance. So I think I'm 2 minutes over time, and I'd like to thank you for listening to my talk. I want to finish just by saying that all the publications and code is available on my website, so please check it out, and I'd be very happy to hear questions and follow-up conversation.
Thank you, Tobias. Any questions?
I have one, Dragan here. So I was just a bit lost when you were presenting the model and the measures, the costs, because the model seemed static. I couldn't see any dynamics there, but later you were showing how some of these estimates sort of, evolve over time. So are you using some sort of kinematic model? I mean, that's the first, what's the model? And then how thetas are related to the model, because your model depends on U and Z, whereas the cost depends on theta. So I was a bit lost there.
Okay, so the forward model is just a robotics simulator, which can provide you with the correct new pose given the state and the current control input. So that's the U's. And the Z's are the states of the robot, so the X, Y position and the kind of rotation of the robot. And then the distances there. Could you repeat your questions about the distances again?
So I mean, what are the thetas? How are thetas related to Z's?
Oh, right. Okay. Sorry. The theta is a they are, let me have some, yes, it's actually not in this slide. Very sorry for that. So the thetas are the rotation that are contained in the Z's. So the Z is X, Y, theta.
Okay.
That's a good point, yeah.
Okay, thank you.
Okay, Toby, Igor has another question for you, Pat.
Dancing eye syndrome. I'm probably don't have the right background to answer that question. So are you asking, oh, right, I think I understand your question. So you want to give a kind of a training signal to people with that syndrome, given the estimates of the given up by our pipeline. Is that right?
Yes, for example, if there is an opportunity to accompany gaze capture with filtering of the relatively high frequency motion of the eyes, then it is possible to make, an image on the computer screen to follow that motion, so that the patient would actually see the normal image without those without the effect.
I see. That's really interesting. I'm not sure whether you can reduce the latency to be low enough for that kind of application area, because that would need to be in the really low milliseconds, I would imagine.
Yes.
But really interesting. I think that there's potential there. It'd be great to chat further about this afterwards, maybe. Yeah.
So it's not about robotics; it's more about humans.
It's not. Absolutely, yeah. It's interesting though. I'm very interested in seeing actual applications of my works. So that's kind of what the wheelchair demonstration work towards. Yes.
Okay. Thanks so much. Thank you.
Okay. Thanks everyone, and thank you, Toby, for the talk. Let's just. Thank you again. Yeah, hang on. There might be. Yeah, everyone's saying thank you. Good.
Thank you.
So
I will hang around for a little longer if there are more questions.
Sure. See you everyone next week. Thanks.
Thank you.